Picture this. At this very moment, you're hurtling through the cosmos at more than 400,000 miles per hour, hitching a ride on a star that's whipping around an absolutely massive black hole. This gravitational monster lives at the heart of our home galaxy, the Milky Way, and it packs 4 million times the punch of our sun. Tonight, we're going to take you on an expedition from our humble Earth all the way to the doorstep of this beast, passing through star graveyards and colossal gas formations that dwarf entire solar systems, witnessing both stellar births and violent deaths. Ready to discover what our galaxy actually looks like? Hit that like button and subscribe, because we're diving in deep. Let's go! Here we are on Earth, but don't be fooled. This rock isn't sitting still for a second. Our whole solar system is bulldozing through space at 67,000 miles per hour, moving faster than any rocket humanity has managed to build. Sure, you might think we're just peacefully circling the sun, but that's only half the picture. The sun itself is dragging us on a much wilder adventure. Imagine our solar system as a speedboat racing across an ocean. The sun's the boat, and every planet is just along for the ride. We're not drifting aimlessly. There's a specific route we follow around our galaxy's core, making one complete circuit every 230 million years. When Earth last occupied this exact galactic position, dinosaurs hadn't even shown up yet. But here's where things get interesting. While we're racing around the galaxy, we're also bouncing up and down like that speedboat hitting waves. Every 33 million years, our solar system crosses through the Milky Way's flat disk, rises above it, then dips below. Some researchers believe these crossings might trigger mass die-offs on Earth. Passing through the galactic disk means encountering more cosmic radiation, asteroid swarms, and gravitational mayhem. It's like driving through different parts of a huge city. Sometimes we're cruising through quiet suburbs with nothing but empty space. Other times, we're speeding through crowded downtown zones packed with stars, gas formations, and cosmic junk. Right now, we're in one of those quieter zones, which might explain why life got its chance to flourish here. What's really wild is that we're not traveling solo. Our solar system sits inside an enormous bubble of hot, thin gas stretching over 1,000 light years in every direction. This bubble got carved out by giant stars that went supernova millions of years ago. Those explosions cleared away most of the thick gas and dust, leaving us in this relatively empty pocket. Without this protective bubble, Earth might look completely different. Dense gas clouds and cosmic radiation could have made it way harder for life to take hold. We're basically living inside the aftermath of ancient stellar violence, cruising through a cavern hollowed out by dying stars. When we look up at the night sky, we're seeing the edge of this bubble in every direction. Those far-off stars are mostly on the opposite side of our cosmic neighborhood, shining through the thin walls of our protective shell. We're like passengers in a glass submarine, traveling through space's deep ocean. Our journey to the galactic center kicks off here in this quiet bubble. But as we venture beyond our solar system, we'll find that our peaceful neighborhood is surrounded by forces and structures that make everything we see from Earth look tiny. The first of these cosmic landmarks sits just beyond our protective bubble, in regions where gas and dust start to thicken and new stars are blazing into existence in spectacular fashion. Astronomers have a name for the bubble around us, the local bubble. This cosmic cavern spans over 1,000 light years across, and we're drifting through it like a dust mote in a cathedral. But this cathedral was carved by violence. About 10 to 20 million years ago, a bunch of massive stars lived and died in this region. When stars 8 times heavier than our sun reach their end, they don't go quietly. They explode as supernovae, unleashing more energy in seconds than our sun will produce in its entire 10 billion year lifetime. These explosions didn't happen just once, they happened repeatedly as star after star reached its violent conclusion. Each supernova blast swept outward like an invisible tsunami, shoving gas and dust away from the explosion site. When multiple supernovae detonate in the same area over millions of years, they create what astronomers call a superbubble. Our local bubble is one of these cosmic hollows, still expanding from those ancient blasts. Think of tossing stones into a calm pond. Each stone creates ripples spreading outward in circles. Now, picture throwing dozens of stones into the same spot over and over. The overlapping ripples would create a complex pattern of waves and calm areas. That's what happened here, except instead of stones and water, we're talking about stellar explosions and the fabric of space itself. The walls of our bubble aren't empty. They're made of hot gas heated to over 1,000,000 degrees by those ancient explosions. This gas is so thin that a cubic inch contains fewer atoms than the best laboratory vacuum on Earth. Yet it glows with X-ray light, invisible to our eyes but detectable by space telescopes. We're not at the center of this bubble. Our solar system is actually closer to one edge, drifting toward a region where the bubble wall is starting to thicken with cooler gas and dust. In about 5 million years, we'll punch through this wall and enter a much denser part of the galaxy. When that happens, our solar system will face new challenges. The thin bubble of hot gas around us acts like a shield, deflecting some cosmic radiation that would otherwise bombard Earth. When we leave this protection and enter denser regions, our planet's atmosphere will encounter more high-energy particles from deep space. Some scientists wonder if this could trigger climate shifts or even mass extinctions. For now, we're sailing through this cosmic safe harbor, protected by the aftermath of stellar death. The irony is perfect. The same explosions that could have sterilized any planets in this region millions of years ago now provide a buffer zone that helped life flourish on Earth. But our peaceful journey through the local bubble is about to encounter something extraordinary. Just ahead, in the direction our solar system is traveling, lie the stellar nurseries where new stars are being born. Just 400 light-years from Earth, something magnificent is unfolding in the darkness. Giant clouds of gas and dust are collapsing under their own gravity, and deep inside these cosmic cocoons, new stars are igniting for the first time. The nearest star-forming region to us is so active that if our eyes could see infrared light, it would glow brighter than any star in our night sky. This stellar nursery is called the Orion Molecular Cloud Complex, and it's a factory for making suns. Picture a cloud of gas and dust so fast that light takes several years to cross from one side to the other. Now imagine that cloud slowly contracting like a giant hand squeezing a sponge. As the cloud shrinks, it heats up. When the center gets hot enough, nuclear fusion kicks in and a new star lights up for the first time. But star birth isn't gentle. When a new star switches on, it blasts out winds of particles at hundreds of miles per second. These stellar winds carve bubbles and caverns in the surrounding gas cloud, creating structures that look like cosmic sculptures. Some of these newborn stars are so massive and energetic that they illuminate entire sections of their birth cloud, creating glowing nebulae visible from thousands of light years away. The process takes millions of years, which sounds long until you realize most stars will shine for billions of years. It's like watching a flower bloom, except the flower is bigger than our solar system and will burn brighter than 1,000,000 suns. Not every clump of gas becomes a star. Some collapse partway and become brown dwarfs, failed stars that glow dimly in infrared light. Others get torn apart by the winds and radiation from their more successful neighbors. What makes this even more remarkable is that stars aren't born alone. When a gas cloud collapses, it usually fragments into dozens or hundreds of pieces, each becoming its own star. These stellar siblings start life clustered together in tight groups, sharing the same cosmic neighborhood. Over millions of years, they gradually drift apart as gravity from the rest of the galaxy pulls them in different directions. Our own sun was born this way, in a cluster with thousands of other stars about 4.5 billion years ago. Those stellar siblings are now scattered across the galaxy, impossible to identify because they've traveled so far from their birthplace. Somewhere out there among the hundreds of billions of stars in the Milky Way are the long-lost brothers and sisters of our sun. The star formation happening in nearby regions gives us a window into our own origins. Every element in your body, except hydrogen and helium, was forged inside a star and scattered into space when that star died. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stellar furnaces that burned billions of years ago. You are literally made of star stuff, assembled from the ashes of cosmic giants. These stellar nurseries are just the beginning of our galactic journey. As we venture further from Earth, we'll encounter the larger structure that contains these star-forming regions. Our solar system doesn't live in just any random part of the galaxy. We're embedded in a structure so vast that early astronomers had no clue it existed. The Orion Arm, also called the local arm, is a minor spiral arm of the Milky Way that stretches for thousands of light years in both directions from our position. We're not just riding along with this structure, we're actually woven into its fabric. Think of the Milky Way galaxy like a massive hurricane seen from space. The bright spiral arms you see in pictures are like the storm's bands of clouds, except instead of water vapor, these arms contain stars, gas, and dust. Most galaxies have 2 or 4 major spiral arms, but they also have smaller arms and spurs branching off the main structure. The Orion Arm is one of these smaller branches. For decades, astronomers thought we lived in a tiny spur connecting 2 major arms, but recent observations have revealed something surprising. The Orion Arm is much larger and more substantial than anyone realized. It extends for over 20,000 light-years, making it a significant galactic feature in its own right. We're not just riding along with this structure, we're actually woven into its fabric. This spiral arm contains some of the most famous objects in our night sky. The bright stars of Orion, Perseus, and Cygnus all belong to our local arm. So do many of the stellar nurseries where new stars are being born, including those vast molecular clouds we just explored. The arm acts like a gravitational river, channeling gas and dust into dense streams where star formation can occur. But spiral arms aren't permanent structures. They're more like traffic jams on a cosmic highway. As material orbits the galaxy, it gets bunched up in certain areas, creating the appearance of spiral patterns. Stars and gas clouds flow into the arms, spend some time there, then flow back out into the spaces between arms. Our solar system has probably drifted in and out of spiral arms multiple times during its journey around the galaxy. The density difference between arms and the spaces between them affects star formation rates across the galaxy. When gas clouds enter a spiral arm, they get compressed by the increased gravitational forces and higher densities. This compression can trigger the collapse of gas clouds into new stars. Then, as massive stars form and eventually explode as supernovae, they can disrupt nearby star formation or trigger even more stellar births. We're currently positioned about halfway between the galaxy's center and its outer edge, in what astronomers call the galactic habitable zone. This might not be a coincidence. Closer to the center, there's too much radiation and gravitational chaos for stable planetary systems. Further out, there aren't enough heavy elements to build rocky planets like Earth. Our location in the Orion Arm puts us in a cosmic sweet spot. As we journey deeper into the galaxy, we'll leave our familiar local arm behind and encounter the much more massive structures that dominate the inner regions of the Milky Way. Hold on to something, because the numbers we're about to share will change how you think about motion forever. You're not just sitting there reading this, you're racing through space faster than a rifle bullet, faster than a jet fighter, faster than anything humans have ever built. And that's just the beginning of your cosmic speed. Right now, Earth is spinning on its axis at over 1,000 miles per hour at the equator. That's your first layer of motion. But Earth is also orbiting the Sun at 67,000 miles per hour, carrying you along for the ride. Most people know about these motions, but they're nothing compared to what comes next. Our entire solar system is orbiting the center of the Milky Way galaxy at 514,000 miles per hour. Let that sink in. Every second, you travel over 140 miles through space, just from galactic rotation. If you could somehow step outside this motion and watch our solar system pass by, we would streak past you faster than a beam of light appears to move to the human eye. But even that's not the full story. Our galaxy itself is moving through space. The Milky Way is falling toward a massive galaxy cluster called the Virgo cluster at over 1 million miles per hour. And the Virgo cluster is being pulled toward an even larger structure called the Great Attractor at incredible speeds. When you add up all these motions, you're traveling through the universe at roughly 1.5 million miles per hour. Think about this. In the time it takes you to read this sentence, you've traveled hundreds of miles through space, and you never felt a thing. There's no cosmic wind in your hair, no sense of acceleration. You're surfing through the universe at mind-bending speeds, and the only reason you don't feel it is because everything around you is moving together. This galactic motion has consequences beyond just impressive numbers. As our solar system orbits the galaxy, we encounter different environments. Sometimes we pass through the galaxy's spiral arms, where star formation is active and radiation levels are higher. Other times we cruise through quieter regions between the arms, like we're doing now. Our orbital speed also means we complete one full trip around the galaxy every 230 million years. Astronomers call this period a galactic year. Since Earth formed, we've completed about 20 galactic years. The last time we were at this exact position in our galactic orbit, the most complex life on Earth was simple marine creatures. Dinosaurs, mammals, and humans have all evolved during our current trip around the galaxy. The Milky Way's rotation isn't uniform. Stars closer to the center orbit faster, while stars at the outer edges move more slowly. This differential rotation is what maintains the galaxy's spiral structure. If everything rotated at the same speed, the spiral arms would wind up too tightly and disappear within a few 100 million years. As we journey further toward the galactic center, we'll encounter regions where these cosmic speeds become even more extreme, and where the effects of our galaxy's rotation create some of the strangest phenomena in the universe. Between the bright stars that light up our night sky lurk the cosmic dead. Scattered throughout our local region of the galaxy are the remnants of stars that burned out long ago, leaving behind objects so strange they seem like science fiction. These stellar corpses are invisible to our eyes, but they're everywhere around us, and some of them are among the most dangerous objects in the universe. The most common stellar graveyard residents are white dwarf stars. These are the dense, hot cores left behind when stars like our Sun reach the end of their lives. A white dwarf packs about 60% of our Sun's mass into a sphere roughly the size of Earth. That means a teaspoon of white dwarf material would weigh as much as a car. The nearest white dwarf to us is only 8.6 light-years away, making it one of our closest stellar neighbors. White dwarfs start incredibly hot, over 100,000 degrees, but they slowly cool down over billions of years. Some of the oldest white dwarfs in our galaxy have been cooling for so long that they're now colder than our Sun's surface. These ancient stellar corpses are like cosmic time capsules, preserving information about stars that died when the universe was young. But white dwarfs can come back to life in spectacular fashion. If a white dwarf has a companion star, it can steal material from its partner through gravitational theft. When enough stolen material builds up on the white dwarf surface, it triggers a thermonuclear explosion called a nova. The explosion blows away the accumulated material, and the process can repeat itself over and over again. Even stranger are the neutron stars hiding in our galactic neighborhood. When a star at least 8 times more massive than our Sun explodes as a supernova, its core can collapse into something almost beyond imagination. A neutron star is so dense that a sugar cube-sized piece would weigh 6 billion tons, more than Mount Everest. The entire star, containing more mass than our Sun, gets crushed into a sphere only about 12 miles across. Some neutron stars spin hundreds of times per second while blasting beams of radiation from their magnetic poles. If those beams sweep across Earth, we detect them as regular pulses of radio waves. These objects, called pulsars, are like cosmic lighthouses with timing so precise they rival atomic clocks. The fastest spinning pulsar known rotates 716 times every second. The magnetic fields around neutron stars are trillions of times stronger than Earth's magnetic field. If a neutron star were placed where our moon is, its magnetic field would erase every credit card on Earth. Getting within 600 miles of one would be instantly fatal, as the magnetic field would disrupt the electrical activity in your nervous system. These stellar graveyards aren't just cosmic curiosities. They're laboratories for studying physics under conditions impossible to create on Earth. They help us understand what happens to matter under extreme gravity, temperature, and magnetic fields. But as remarkable as these stellar corpses are, they're just appetizers for what awaits us as we venture deeper into the galaxy. As we leave our local spiral arm behind and venture deeper into the galaxy, we encounter something that dwarfs our cosmic neighborhood. The Perseus arm is one of the Milky Way's major spiral arms, a galactic superhighway packed with more stars, gas, and cosmic activity than anything we've seen so far. It's like stepping from a quiet suburban street onto a busy interstate. This massive structure contains some of the most luminous and energetic stars in our galaxy. While our local arm is home to relatively modest stars and star-forming regions, the Perseus arm hosts stellar monsters. Stars here can be 50 or even 100 times more massive than our Sun, burning so bright and hot that they appear blue-white to our telescopes. These giants live fast and die young, typically burning out in just a few million years. The Perseus arm gets its name from the constellation Perseus, which lies in the same direction when viewed from Earth. But this spiral arm extends far beyond what we can see with the naked eye. It stretches for tens of thousands of light years, wrapping partway around the galaxy like a loosely coiled spring. If you could shrink the Milky Way down to the size of a dinner plate, the Perseus arm would be one of the major lines you'd see spiraling outward from the center. What makes spiral arms like Perseus so active? They're regions where the galaxy's density wave patterns pile up gas and dust, creating the perfect conditions for massive star formation. Think of it like a traffic jam on a highway. Cars bunch up in certain areas, move slowly through the jam, then spread out again on the other side. Gas clouds do the same thing as they orbit the galaxy, getting compressed when they enter spiral arms and triggering bursts of star formation. The Perseus arm contains some of the most spectacular stellar nurseries known to astronomy. One of them, called the Eagle Nebula, is famous for the towering pillars of gas and dust where new stars are being born. These pillars stretch for several light years and are being carved by the intense radiation from nearby massive stars. Another region, the Rosette Nebula, glows bright red from ionized hydrogen gas heated by a cluster of hot young stars at its center. But the Perseus arm isn't just about starbirth. It's also home to some of the most violent stellar deaths. When those massive blue stars reach the end of their brief lives, they explode as supernovae with the energy of billions of suns. These explosions can be seen from other galaxies millions of light years away. They also inject heavy elements into space, enriching the surrounding gas with the building blocks needed for rocky planets and potentially life itself. Traveling through the Perseus arm would be like driving through a cosmic construction zone. Everywhere you look, there's activity. Stars being born, stars exploding, gas clouds colliding and merging, intense radiation fields that would sterilize any unprotected spacecraft. It's beautiful and deadly at the same time. As we continue our journey toward the galactic center, we'll encounter even more massive structures and more extreme conditions. Imagine looking up at the night sky and seeing not just individual stars, but entire cities of them packed so tightly together they look like glowing clouds. As we journey deeper into the galaxy, we encounter star clusters containing hundreds of thousands, even millions of stars, all born from the same cosmic nursery. These stellar cities are some of the most spectacular and crowded places in the Milky Way. The most massive star clusters in our galaxy are called globular clusters, and they're ancient beyond imagination. These spherical collections of stars formed when the universe was young, over 12 billion years ago. A single globular cluster can contain 1 million stars packed into a space just a few hundred light years across. If Earth orbited a star in the center of a globular cluster, our night sky would contain thousands of stars brighter than Venus, turning night into a brilliant twilight. Picture the density difference. In our solar neighborhood, the nearest star is over 4 light years away. In the core of a globular cluster, stars can be separated by distances smaller than our solar system. If our sun lived in such a crowded environment, we might have dozens of neighboring stars closer than Pluto. The gravitational interactions between all these stars would make planetary orbits chaotic and unstable. But globular clusters aren't the only stellar cities in our galaxy. Scattered through the galactic disk are open clusters, younger groups of stars that formed more recently from the same gas cloud. The most famous open cluster visible to the naked eye is the Pleiades, also called the Seven Sisters. This cluster contains over 1,000 stars, all born within the last 100 million years from a single molecular cloud. Open clusters are stellar nurseries we can observe in action. Unlike ancient globular clusters, where star formation ended billions of years ago, some open clusters are still embedded in the gas and dust clouds where they formed. We can watch new stars igniting while others are still condensing from the surrounding material. It's like seeing a cosmic city under construction. These stellar cities don't last forever. Over hundreds of millions of years, gravitational interactions with other stars and gas clouds gradually strip away the cluster members. Stars get kicked out of the group and become isolated wanderers like our sun. Most open clusters dissolve completely within 1 billion years, scattering their stars across the galaxy. The stars in these clusters are like cosmic laboratories for testing our understanding of stellar evolution. Since all the stars in a cluster formed at the same time from the same material, they provide perfect natural experiments. Astronomers can compare how stars of different masses evolve by studying cluster members of various sizes and weights. Some of the most massive star clusters in our galaxy are so packed with giant stars that they're called superstar clusters. These regions contain dozens of stars over 50 times more massive than our sun, all crowded into areas smaller than our solar system. The radiation and stellar winds from these monsters create some of the most extreme environments in the galaxy. As we venture even deeper toward the galactic center, we'll discover that these impressive star clusters are just a preview of the cosmic chaos that awaits us. Between the stars flows an invisible ocean. Most people think of space as empty, but it's actually filled with vast streams of gas and dust that flow between spiral arms like cosmic rivers. These interstellar currents are invisible to our eyes, but they shape the evolution of our entire galaxy, carrying the raw materials for star formation from one region to another. These gas streams aren't randomly scattered through space. They follow specific patterns created by the galaxy's rotation and gravitational forces. As the Milky Way spins, differential rotation causes gas clouds to stretch and shear, creating long filaments that can extend for thousands of light years. Think of it like stirring honey into coffee. The stirring motion creates spiral patterns and streams that follow the direction of rotation. The composition of these interstellar rivers tells the story of stellar life and death across the galaxy. Most of the gas is hydrogen and helium left over from the Big Bang, but mixed throughout are heavier elements forged inside stars and scattered by supernova explosions. Carbon, oxygen, silicon, iron, and dozens of other elements flow through these cosmic currents, gradually enriching different regions of the galaxy with the building blocks of rocky planets. Some of these rivers flow inward toward the galactic center, while others spiral outward toward the galaxy's edge. The inward flowing streams feed the massive star formation regions near the galactic core. The outward flowing currents carry processed material from the crowded inner galaxy to the quieter outer regions where our solar system lives. Over billions of years, this circulation has gradually redistributed elements throughout the Milky Way. But these aren't gentle, steady flows. The interstellar medium is turbulent and chaotic, stirred by stellar winds, supernova explosions, and gravitational forces from massive stars and star clusters. Shockwaves from stellar explosions can trigger the collapse of nearby gas clouds, starting new cycles of star formation. Other shockwaves can disrupt star formation by heating and dispersing the raw materials before they can condense. The temperature variations in these gas streams create a complex ecosystem of interstellar environments. Some regions contain hot, thin gas heated to millions of degrees by supernova explosions. Other areas harbor cold, dense molecular clouds, where temperatures drop to just a few degrees above absolute zero. These molecular clouds are the nurseries where new stars form, but they make up only a small fraction of the total interstellar volume. The magnetic fields threading through these gas streams add another layer of complexity. These fields, though incredibly weak by terrestrial standards, can guide the flow of charged particles and influence how gas clouds collapse to form stars. They also accelerate cosmic rays, high-energy particles that travel throughout the galaxy at nearly the speed of light. As our journey takes us closer to the galactic center, these interstellar rivers become more turbulent and energetic. The gas densities increase, the magnetic fields strengthen, and the rate of star formation accelerates dramatically. We're approaching regions where the calm interstellar medium of our local neighborhood gives way to the cosmic maelstrom surrounding the galaxy's heart. The next major structure we'll encounter represents a dramatic escalation in scale and violence. We've now reached one of the galaxy's true giants. The Scutum Centaurus arm is the longest and most massive spiral arm in the Milky Way, a cosmic structure so vast it wraps more than halfway around the entire galaxy. If the Perseus arm was a busy highway, this is a superhighway, carrying the bulk of our galaxy's star formation and stellar activity. This massive arm gets its name from two constellations visible from Earth, Scutum and Centaurus. But those tiny patches of sky barely hint at the true scale of this structure. The Scutum Centaurus arm extends for over 60,000 light-years, making it longer than the distance from Earth to the galactic center. It contains some of the most active star-forming regions in the entire galaxy. What makes this arm so special is its proximity to the galactic center. As one of the inner spiral arms, it receives a constant flow of gas and dust from the galaxy's central regions. This material gets funneled along the arm's length, creating an almost continuous chain of stellar nurseries and massive star clusters. The arm acts like a cosmic assembly line for manufacturing stars. The star formation rate in the Scutum Centaurus arm is staggering. In some regions, new stars are being born at rates thousands times higher than in our quiet local neighborhood. These aren't just ordinary stars either. The arm specializes in producing stellar monsters, stars with masses 50 to 100 times greater than our Sun. When these giants explode as supernovae, they can outshine entire galaxies for weeks. One of the most remarkable features of this arm is the Scutum star cloud, a dense concentration of stars visible to the naked eye as a bright patch in the constellation Scutum. This region contains some of the most luminous stars known, including red supergiants so large they could swallow the orbit of Mars if placed at the center of our solar system. These stellar behemoths burn through their nuclear fuels so quickly that they live for only a few million years before exploding. The density of matter in the Scutum Centaurus arm creates a gravitational playground where massive stars and star clusters interact in complex ways. Stars can be ejected from clusters at high speeds, becoming runaway stars that race through the galaxy. Some of these stellar refugees travel so fast, they'll eventually escape the Milky Way entirely, becoming lonely wanderers in intergalactic space. But perhaps the most impressive aspect of this arm is how it channels material toward the galactic center. Gas clouds flowing along the arm's length eventually reach the galaxy's central regions, where they encounter gravitational forces and conditions unlike anywhere else in the Milky Way. This feeding process has been going on for billions of years, gradually building up the massive structures we'll encounter at the galaxy's heart. As we follow these gas streams deeper into the galaxy, we're approaching a region where the normal rules of stellar physics begin to break down. The gravitational forces become so strong and the density so extreme that matter behaves in ways impossible anywhere else in our cosmic neighborhood. The next structure we encounter will challenge everything we think we know about how galaxies work. Hidden at the heart of our galaxy lies a secret that astronomers only discovered in recent decades. The Milky Way isn't just a simple spiral galaxy. At its center stretches a massive bar-shaped structure made of stars and gas, invisible from Earth but larger than anything we've encountered so far. This galactic bar is the hidden backbone that controls the flow of matter throughout our entire galaxy. Picture the Milky Way from above, and instead of seeing neat spiral arms emerging from a circular center, you'd see something that looks more like a cosmic barbell. The galactic bar stretches for over 27,000 light-years from end to end, making it roughly half the diameter of the entire galactic disk. This massive structure rotates as a single unit, spinning faster than the surrounding spiral arms. The bar formed billions of years ago through a process called bar instability. As the galaxy aged and stars settled into more circular orbits, gravitational interactions between stars began creating elongated patterns. Over hundreds of millions of years, these patterns grew stronger until they formed the rigid bar structure we see today. About 2/3 of all spiral galaxies have similar bars at their centers. But this isn't just a static structure. The galactic bar acts like a cosmic pump, channeling gas from the outer galaxy toward the center through a process called gravitational torquing. As gas clouds orbit the galaxy and encounter the bar's gravitational field, they get deflected from circular orbits into elongated paths that spiral inward. It's like water flowing down a drain, except the drain is 27,000 light-years long. This inward flow of gas has profound consequences for the entire galaxy. The bar has been feeding material to the galactic center for billions of years, building up the massive structures and dense stellar populations we find there. Without the bar's pumping action, the central regions of our galaxy would be much quieter and less active places. The bar also affects the motion of stars throughout the galaxy. Stars that venture too close to the bar can get gravitationally scattered onto new orbits, sometimes being flung toward the galactic center or ejected toward the outer regions. Our own solar system may have encountered the bar's influence during its journey around the galaxy, though we're currently in a safe region, well outside the bar's direct effect. Recent observations have revealed that the galactic bar isn't perfectly smooth. It contains its own spiral structure, with dense lanes of gas and dust wrapped around the bar's length like cosmic DNA strands. These bar spirals are some of the most active star-forming regions in the galaxy, powered by the constant inflow of fresh material from the outer regions. The bar's rotation rate is precisely tuned to maintain the galaxy's spiral structure. If it rotated too fast or too slow, the spiral arms would either wind up too tightly or unwind completely within a few 100 million years. This delicate balance has kept the Milky Way's basic structure stable for billions of years. As we follow the bar's gravitational channels toward the galactic center, we're approaching regions where the density of stars and gas reaches truly extreme levels. As we approach the inner galaxy, the space between stars transforms into something almost unrecognizable. Here lurk molecular clouds so massive they dwarf entire solar systems, cosmic titans containing enough raw material to build millions of stars. These aren't the modest stellar nurseries we found in our local neighborhood. These are the galaxy's heavy industry zones, where star formation happens on a scale that defies comprehension. The largest of these giants is called Sagittarius B2, a molecular cloud complex located just 300 light-years from the galactic center. This single cloud contains enough material to build 3 million stars like our Sun. If you could somehow compress our entire solar system down to the size of a marble, Sagittarius B2 would still be larger than a football stadium. The cloud is so massive that its gravitational pull affects the orbits of nearby stars. But size isn't the only thing that makes these clouds remarkable. The conditions inside them are unlike anything in our quiet corner of the galaxy. Temperatures drop to just 10 degrees above absolute zero, making them some of the coldest places in the universe. At these frigid temperatures, hydrogen atoms stick together to form hydrogen molecules, creating a dense fog of gas and dust particles. The chemistry happening inside these clouds reads like a cosmic cookbook. Over 150 different molecules have been detected in interstellar space, from simple water and carbon monoxide to complex organic compounds that could serve as the building blocks for life. Some clouds contain vast quantities of ethyl alcohol, enough to fill Earth's oceans. Others harbor molecules that smell like raspberries or taste like rum. These molecular giants don't just sit passively in space. They're constantly being stirred and heated by radiation from nearby stars, shock waves from supernova explosions, and magnetic fields that thread through the galaxy. This turbulence creates a complex internal structure with dense cores, expanding shells, and streaming flows of material. The clouds are like cosmic weather systems, complete with their own storms and circulation patterns. When sections of these clouds become dense enough, gravity takes over and triggers collapse. But the collapse doesn't happen all at once. Different parts of the cloud collapse at different rates, creating a cascade of star formation that can last for millions of years. The most massive regions collapse first, forming the giant stars that will eventually explode and trigger more collapse in neighboring areas. The scale of star formation in these regions can be breathtaking. A single molecular cloud complex can give birth to thousands of stars simultaneously, creating massive stellar associations that outshine entire galaxies. Some of the most luminous star-forming regions in the known universe are powered by molecular clouds near galactic centers. As we venture deeper into the galaxy's heart, these molecular titans become even more extreme. The densities increase, the gravitational forces strengthen, and the rate of star formation reaches levels that would sterilize any nearby planetary systems with radiation. We're approaching the galaxy's central molecular zone, where the normal rules of star formation break down completely. Welcome to the most extreme neighborhood in our galaxy. The central molecular zone is a ring of molecular clouds surrounding the Milky Way's center, and it's unlike anywhere else we've visited. Here, just a few hundred light years from our galaxy's supermassive black hole, the laws of physics are pushed to their absolute limits. This is where cosmic violence and stellar birth collide in ways that would be impossible anywhere else in the galaxy. The entire central molecular zone spans about 1,000 light years across, but contains as much gas and dust as the rest of the inner galaxy combined. That's enough raw material to build 10 million stars like our Sun, all packed into a region that represents less than 1% of the galactic disk's area. If our local region of space has the density of air, the central molecular zone has the density of water. But despite containing enough material to trigger explosive star formation, this region is surprisingly quiet. The star formation rate here is actually 10 to 100 times lower than it should be based on the available gas supply. Something is preventing these massive molecular clouds from collapsing into stars, and astronomers are still trying to understand why. The answer lies in the extreme conditions near the galactic center. Intense magnetic fields heated by the supermassive black hole and thousands of massive stars thread through the molecular clouds like invisible steel cables. These fields are strong enough to support the clouds against gravitational collapse, preventing the normal cascade of star formation we see elsewhere in the galaxy. When star formation does happen here, it produces some of the most massive stars known to exist. These stellar monsters can be over 100 times more massive than our Sun, burning so hot and bright that they appear blue-white even from thousands of light years away. They live fast and die young, typically exploding as supernovae within just a few million years of their birth. The temperatures in this region tell a story of cosmic violence. While the dense molecular cloud cores remain cold, the spaces between clouds are filled with gas heated to millions of degrees by shock waves from stellar explosions and energy from the central black hole. This creates a bizarre environment where freezing cold molecular gas exists just light years away from plasma hot enough to strip electrons from atoms. Magnetic field strengths here are thousands of times stronger than anything in our solar neighborhood. These fields accelerate particles to incredible speeds, creating streams of cosmic rays that race throughout the galaxy. Some of these high-energy particles eventually reach Earth, where they're detected by cosmic ray observatories as showers of subatomic particles in our atmosphere. The central molecular zone acts like a massive reservoir, storing gas and dust that occasionally gets funneled even closer to the galactic center. When gravitational instabilities or stellar explosions disrupt the delicate balance, streams of material spiral inward toward the supermassive black hole, triggering bursts of activity that can be detected across the electromagnetic spectrum. As we venture deeper into this cosmic maelstrom, we're approaching the point of no return. Deep in the heart of our galaxy, something is broadcasting. Radio telescopes on Earth detect a constant stream of signals coming from the galactic center, electromagnetic messages that carry information about conditions no human will ever experience firsthand. These radio waves have traveled 26,000 light-years to reach us, bringing news from the most violent place in our cosmic neighborhood. The signals tell a story of chaos. Unlike the steady radio emissions from normal stars, the galactic center broadcasts in bursts and flares that can change intensity within minutes. Sometimes the signal strength increases by factors of hundreds or thousands, then fades back to normal levels. These fluctuations are the radio signatures of matter falling into our galaxy's central black hole, screaming its final electromagnetic distress call before disappearing forever. But the central black hole isn't the only radio source in this crowded region. Scattered throughout the galactic center are dozens of compact radio sources, each one a cosmic lighthouse, beaming energy in all directions. Some of these are neutron stars, the ultra-dense remnants of massive stellar explosions. Others are stellar mass black holes, smaller cousins of the central monster that are actively feeding on nearby gas and dust. The most mysterious radio signals come from long, thin structures called non-thermal filaments. These cosmic threads stretch for hundreds of light years through the galactic center, glowing brightly in radio wavelengths but remaining completely invisible to optical telescopes. Scientists think they're illuminated by high-energy electrons spiraling through powerful magnetic fields, but their exact nature remains one of astronomy's unsolved puzzles. Radio observations have also revealed the skeletal structure of gas flows near the galactic center. Hot, ionized gas streams spiral inward toward the central black hole, creating curved radio arcs that map out the gravitational field's influence. These gas streams don't fall straight in. Instead, they follow complex orbital paths, sometimes orbiting the black hole multiple times before finally crossing the point of no return. One of the most dramatic radio discoveries was the detection of massive gas clouds being torn apart by the central black hole's gravity. Astronomers watched in real time as a cloud called G2, containing about 3 times Earth's mass, stretched into a long stream as it approached the black hole. The radio emissions tracked the cloud's destruction over several years, providing a front-row seat to gravitational violence on a cosmic scale. The radio waves also reveal the presence of a hot, thin atmosphere surrounding the galactic center. This gas has been heated to millions of degrees by shock waves from stellar explosions and energy from the central black hole. The radio emissions from this superheated gas create a glowing halo around the galaxy's heart, visible only to radio telescopes. Perhaps most remarkably, radio observations have detected relativistic jets emanating from the galactic center. These are narrow beams of matter and energy traveling at nearly the speed of light, blasted outward by magnetic fields near the black hole. The jets extend for thousands of light years above and below the galactic plane, carrying energy and particles far from their point of origin. These radio signals are our only way to peer through the dust and gas that shrouds the galactic center from optical view, providing a window into the most extreme physics playground in our galaxy. At the very heart of our galaxy, packed into a space smaller than the distance from Earth to our nearest stellar neighbor, live over 25 million stars. This is the nuclear star cluster, the densest collection of stars in the Milky Way and one of the most crowded places in the known universe. If our solar system existed here, the night sky would contain thousands of stars brighter than our full moon. The stellar density in this region defies imagination. While the nearest star to our Sun is over 4 light-years away, stars in the nuclear star cluster can be separated by distances smaller than our solar system. In the very center, stellar neighbors might be only a few billion miles apart, close enough that their outer atmospheres could interact during close approaches. Planetary systems would be impossible here. The gravitational chaos would tear apart any orbiting worlds within thousands of years. But these aren't ordinary stars crowding together. Many of the cluster's residents are stellar exotics, objects that form only under the most extreme conditions. Wolf-Rayet stars burn so hot they blast away their outer layers in stellar winds traveling thousands of miles per second. Red supergiants swell to sizes larger than Earth's orbit around the Sun. Blue hypergiants shine with the luminosity of millions of suns. burning through their nuclear fuel so rapidly they'll explode within a few million years. The gravitational environment here operates by different rules than anywhere else in the galaxy. Stars don't follow simple elliptical orbits like planets around the sun. Instead, they trace complex rosette patterns as they're tugged by the combined gravity of millions of neighbors and the supermassive black hole at the center. Some stars follow such elongated orbits that they swing from the cluster's edge nearly to the black hole's event horizon and back again. The cluster formed through a process that took billions of years. As gas flows spiraled inward toward the galactic center, they triggered bursts of star formation in the dense environment near the supermassive black hole. Over time, these stellar generations built up into the massive cluster we see today. But star formation here wasn't a gradual process. It happened in violent episodes triggered by major gas infall events, creating distinct populations of stars with different ages and compositions. Life cycles here are compressed and accelerated. Massive stars form, live, and die within just a few million years, their supernova explosions adding to the chaos. The cluster contains dozens of stellar mass black holes, neutron stars, and white dwarfs, all packed into the same small volume with the living stars. When these compact objects encounter each other, they can spiral together and merge, creating gravitational wave signals that ripple across the universe. The nuclear star cluster acts like a natural particle accelerator, using gravitational slingshot effects to launch stars at incredible velocities. Some stars get ejected from the cluster at speeds exceeding 1,000 miles per second, fast enough to escape the galaxy entirely. These hypervelocity stars have been detected racing through the Milky Way's outer regions, stellar refugees from the galactic center's gravitational violence. At the cluster's heart lies the source of all this chaos, our galaxy's supermassive black hole. At the absolute center of our galaxy lurks a monster, Sagittarius A star, pronounced A star. The supermassive black hole at the Milky Way's heart contains the mass of 4 million suns crushed into a space smaller than Mercury's orbit. This cosmic giant sits perfectly still at the galaxy's gravitational center, while 200 billion stars orbit around it like moths circling a flame. It's the anchor point that holds our entire galaxy together. For decades, astronomers suspected this monster existed, but couldn't prove it. The galactic center is hidden behind vast clouds of dust that block visible light, making direct observation impossible. But in the 1990s, astronomers began tracking individual stars near the galactic center using infrared telescopes that could peer through the dust. What they discovered changed our understanding of black holes forever. The stars closest to Sagittarius A star follow elliptical orbits so extreme they stretch the laws of physics. One star, designated S2, completes an orbit around the black hole every 16 years. At its closest approach, it races past the black hole at over 25 million miles per hour, traveling fast enough to cross the distance from Earth to the Moon in just 30 minutes. The gravitational forces at this distance are so intense, they cause measurable effects predicted by Einstein's theory of relativity. But Sagittarius A star isn't content to sit quietly. Though it appears calm most of the time, the black hole occasionally flares with activity when gas or debris falls too close. These feeding events can increase the black hole's brightness by factors of hundreds within minutes as matter spirals inward and heats to billions of degrees before disappearing forever. The energy released during these flares can outshine all the stars in the nuclear star cluster combined. The black hole's event horizon, the boundary beyond which nothing can escape, has a diameter of about 15 million miles. That might sound large, but it's actually tiny compared to the black hole's sphere of influence, which extends for several light years in all directions. Within this region, the black hole's gravity dominates everything, controlling the motion of stars, gas clouds, and even light itself. Perhaps the most remarkable discovery about Sagittarius A asterisk came in recent years, when astronomers captured the first direct image of the black hole's shadow. Using a planet-sized network of radio telescopes working together, they photographed the dark silhouette of the event horizon, surrounded by a glowing ring of superheated gas. The image confirmed decades of theoretical predictions about how black holes should appear. The magnetic field around Sagittarius A asterisk is millions of times stronger than Earth's magnetic field. This intense magnetism accelerates particles to nearly the speed of light and launches them in narrow jets extending thousands of light years above and below the galactic plane. These jets carry energy and matter far from the black hole, influencing star formation and gas dynamics throughout the galaxy. Every star in our galaxy, including our Sun, is ultimately orbiting this central monster. Though we're 26,000 light-years away, Sagittarius A asterisk's gravity reaches across the galaxy to guide our motion through space. The black hole's event horizon represents the ultimate frontier, where space and time themselves break down. We've reached the edge of everything. The event horizon of Sagittarius A asterisk marks the boundary where the normal rules of physics surrender to something far stranger. Cross this invisible line and you've entered a region of space from which nothing, not matter, not light, not information itself, can ever return. It's the ultimate point of no return, a one-way membrane between our universe and whatever lies beyond. The event horizon isn't a physical surface you could touch or stand on. It's a mathematical boundary defined by gravity so intense that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing can escape once it crosses this line. The horizon appears as a perfect sphere surrounding the black hole, with a diameter of roughly 15 million miles, large enough to contain the orbits of Mercury and Venus if the black hole sat where our Sun is located. But here's where things get weird. If you somehow approached the event horizon, what you experience would depend entirely on your point of view. To an outside observer watching your journey, you would appear to slow down as you approached the horizon. Your image would redshift to longer and longer wavelengths until you faded from view, seemingly frozen at the horizon's edge forever. Time dilation would stretch your final moments into an eternity from the outside perspective. Your experience would be completely different. From your point of view, you would pass through the event horizon normally, with no special sensation marking the moment you crossed the point of no return. You might not even realize you'd crossed it until you tried to turn around and discovered that every direction now pointed toward the black hole's center. The horizon would be invisible to you, just empty space that happened to have a special property. The space near the event horizon warps in ways that defy everyday understanding. Tidal forces here are so extreme they would stretch any object that got too close, pulling it apart at the atomic level in a process astronomers call spaghettification. Your feet would experience significantly stronger gravity than your head, stretching you into a long, thin shape before tearing you apart completely. Time itself behaves strangely near the event horizon. The intense gravitational field causes time to run slower compared to regions farther from the black hole. A clock at the horizon would tick at a different rate than one in normal space. This effect, called gravitational time dilation, means that the black hole exists in a different temporal reference frame than the rest of the galaxy. The horizon also marks the boundary where space-time curvature becomes infinite. At the center of the black hole lies what physicists call a singularity, a point where density becomes infinite and the laws of physics as we understand them break down completely. The event horizon shields the rest of the universe from direct contact with this cosmic impossibility. Recent theories suggest that black hole event horizons might not be as absolute as once thought. Quantum effects near the horizon could allow some information to escape through a process called Hawking radiation. But these effects are so tiny, they're undetectable for supermassive black holes like Sagittarius A star. Beyond the event horizon lies territory that challenges the very foundations of our understanding of reality. From the supermassive black hole at our galaxy's heart, two invisible spears of energy pierce through space at 99% the speed of light. These relativistic jets extend for thousands of light years above and below the galactic plane, carrying matter and energy far from the black hole's grip in one of the most spectacular displays of cosmic power in the universe. What makes them even more remarkable is that they originate from something that supposedly allows nothing to escape. The jets don't actually come from inside the black hole's event horizon. Instead, they're launched from the swirling disk of superheated gas and plasma spiraling into the black hole. As this material falls inward, it gets compressed and heated to billions of degrees, creating conditions more extreme than the core of any star. Magnetic fields threading through this accretion disk get twisted and amplified until they become powerful enough to launch streams of particles at relativistic speeds. Think of the magnetic field lines like rubber bands being twisted tighter and tighter. Eventually, they snap back with tremendous force, accelerating charged particles along narrow channels that extend far from the black hole. These jets are incredibly narrow, maintaining their focus across thousands of light years, with a precision that would be impossible through any human technology. The jets from Sagittarius A star are relatively weak compared to those from more active supermassive black holes in other galaxies. Some galactic jets are so powerful they can be detected from billions of light years away, outshining all the stars in their host galaxies combined. Our galaxy's central black hole is currently in a quiet phase, producing jets that are barely detectable even with our most sensitive instruments. But even these weak jets carry enormous amounts of energy. The particles racing along them have been accelerated to energies millions of times higher than anything achievable in human-built particle accelerators. When these high-energy particles interact with magnetic fields or matter along their path, they produce gamma rays, the most energetic form of electromagnetic radiation in the universe. The jets also serve as cosmic particle accelerators, creating some of the highest energy cosmic rays that bombard Earth's atmosphere. These particles travel so fast that time dilation effects become significant. A particle in one of these jets experiences time passing much more slowly than we do, meaning its journey across the galaxy takes only minutes or hours from its own perspective, even though thousands of years pass in our reference frame. Recent observations have revealed that the jets from Sagittarius A star change direction over time. The black hole's rotation axis doesn't always point in the same direction, causing the jets to wobble like water from a spinning sprinkler. This precession occurs over timescales of thousands of years, slowly sweeping the jets across different regions of the galaxy. The jets also interact with the surrounding interstellar medium, creating shock waves and heating gas clouds they encounter along their path. This process helps regulate star formation in the galaxy by injecting energy into molecular clouds that might otherwise collapse to form new stars. These relativistic beacons represent the black hole's most visible influence on the galaxy around it, extending its reach far beyond the gravitational prison of the event horizon. Near the supermassive black hole at our galaxy's center, time itself becomes a variable. The intense gravitational field warps the fabric of space-time so severely that clocks run slower, distances stretch, and the fundamental nature of reality bends in ways that would seem impossible anywhere else in the universe. Welcome to the realm where Einstein's wildest theories become everyday physics. This time-warping effect, called gravitational time dilation, means that time passes differently depending on how close you are to the black hole. A clock placed just outside the event horizon would tick significantly slower than an identical clock in normal space. From our perspective on Earth, 26,000 light-years away, that clock would appear almost frozen, its hands barely moving as gravity stretches each second into an eternity. The effect isn't subtle. Near Sagittarius A star, at the black hole's event horizon, time dilation becomes infinite from an outside observer's perspective. This means that anything falling toward the black hole would appear to slow down dramatically as it approached the horizon, its image redshifting and fading until it became invisible, seemingly frozen at the edge of forever. But the time warping extends far beyond the event horizon itself. Stars orbiting close to the black hole experience measurable time dilation effects. The star S2, which we encountered earlier racing around the black hole every 16 years, actually ages slightly slower than it would if it orbited farther away. Over millions of years, this difference could add up to thousands of years of extrastellar lifetime. The warping of time is intimately connected to the warping of space. Near the black hole, space itself becomes curved, like a bowling ball creating a depression in a stretched rubber sheet. This curvature affects not just the passage of time, but also the paths that light and matter must follow. Straight lines in normal space become curved trajectories in the black hole's vicinity. One of the most mind-bending consequences of this space-time warping is the existence of closed time-like curves. In certain regions near rotating black holes, it becomes theoretically possible for a path through space-time to loop back on itself, potentially allowing travel into the past. However, these exotic paths exist only in the most extreme gravitational environments and would require surviving conditions that would destroy any known form of matter. The time dilation effects near Sagittarius A star also influence the light we receive from objects in that region. Radio signals from gas clouds spiraling into the black hole arrive at Earth with their frequencies shifted by the gravitational field. This gravitational redshift provides astronomers with a direct measurement of the black hole's mass and the strength of its gravitational field. Perhaps most remarkably, the time warping around supermassive black holes might help explain some of the biggest mysteries in cosmology. Some theories suggest that the extreme space-time curvature near black holes could be connected to the expansion of the universe itself, linking the smallest and largest scales of cosmic physics. As we pull back from this region where time itself bends and breaks, we begin to see how our entire galaxy is embedded in an even larger and more mysterious structure. Our entire galaxy is embedded inside something invisible and mysterious. Surrounding the Milky Way's visible stars and gas clouds is a massive spherical halo made of dark matter, a substance that outweighs everything we can see by a factor of 10 to 1. This dark halo extends far beyond the galaxy's spiral arms, creating an invisible architecture that holds our cosmic home together and determines how it moves through the universe. Dark matter doesn't emit, absorb, or reflect light of any kind. It's completely invisible to every form of electromagnetic radiation, from radio waves to gamma rays. The only way we know it exists is through its gravitational effects on the visible matter around it. Stars in the outer regions of galaxies orbit faster than they should based on the visible mass alone. Something with tremendous gravitational pull must be holding them in their orbits. The Milky Way's dark halo is enormous, extending out to distances of at least 600,000 light-years from the galactic center. That's 3 times larger than the visible galaxy, and large enough to encompass several of our satellite galaxies. If you could somehow see dark matter, our galaxy would look like a small, bright disk floating at the center of a much larger, diffuse sphere. This invisible halo contains roughly 1 trillion solar masses worth of dark matter, making it by far the most massive component of our galactic system. All the stars, gas, dust, and planets in the Milky Way combined represent only about 15% of the total mass. We're essentially living inside a dark matter structure with some normal matter sprinkled on top, like seasoning on a vast cosmic meal. The dark halo isn't perfectly smooth. Computer simulations suggest it contains substructure, with clumps and streams of dark matter flowing through it. Some of these dark matter clumps might be the remnants of smaller galaxies that were torn apart by the Milky Way's gravity billions of years ago. Others could be primordial structures that formed in the early universe and survived to the present day. The nature of dark matter remains one of the biggest unsolved mysteries in science. Leading candidates include exotic particles that interact only through gravity and the weak nuclear force, making them nearly impossible to detect directly. Laboratory experiments around the world are searching for signs of these particles, but so far, dark matter continues to live up to its name. The dark halo also plays a crucial role in how our galaxy formed and evolved. In the early universe, dark matter clumped together first, creating gravitational wells that attracted normal matter. Gas fell into these dark matter halos and eventually formed the first stars and galaxies. Without dark matter's gravitational scaffolding, galaxies like the Milky Way could never have formed. Our motion through the dark halo creates a cosmic wind of dark matter particles streaming through the solar system at hundreds of kilometers per second. This dark matter wind is completely undetectable to our senses, but it represents one of the most abundant forms of matter in the universe, flowing past us every second. Beyond our galaxy's dark halo lie even larger structures that dwarf everything we've encountered so far. Our galaxy is not alone. Orbiting the Milky Way like cosmic moons around a planet are dozens of smaller galaxies, gravitational captives locked in eternal dance with our galactic giant. These satellite galaxies range from tiny collections of a few million stars to substantial stellar cities containing billions of suns. Together, they form a complex gravitational ecosystem that has been evolving for billions of years. The most famous of our satellite galaxies are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere as fuzzy patches of light. The Large Magellanic Cloud contains about 30 billion stars, making it roughly 1/10 the mass of the Milky Way. Its smaller companion harbors around 3 billion stars, still massive enough to support active star formation and its own internal spiral structure. But these prominent satellites are just the beginning. Astronomers have discovered over 50 smaller satellite galaxies orbiting the Milky Way, with names like Draco, Ursa Minor, and Sagittarius. Most of these are dwarf galaxies, containing anywhere from a few thousand to a few billion stars. They're spread across the sky in all directions, some as close as 75,000 light-years and others as distant as 3 million light-years from our galactic center. The relationship between the Milky Way and its satellites is complex and often violent. Our galaxy's superior gravitational pull strips stars and gas from smaller companions that venture too close. The Sagittarius dwarf galaxy is currently being torn apart by this process, leaving long streams of stars scattered across our sky. Over hundreds of millions of years, these stellar streams will be completely absorbed into the Milky Way's outer regions. Some satellite galaxies show signs of multiple episodes of star formation, triggered by close encounters with our galaxy. As they swing through their elliptical orbits, gravitational forces compress their internal gas clouds, sparking bursts of new stellar birth. These interactions create irregular patterns of stellar ages within the satellites, like geological layers recording their orbital history. The satellite galaxies also serve as laboratories for studying dark matter. Many of these small galaxies appear to be dominated by dark matter, with visible stars making up only a tiny fraction of their total mass. Some satellites are so dark matter rich that they barely have enough normal matter to trigger star formation, existing as invisible gravitational ghosts with just a handful of stars marking their presence. The distribution of satellite galaxies around the Milky Way isn't random. They tend to lie in a flattened, disk-like structure, rather than being scattered spherically around us. This unexpected pattern has challenged our understanding of how galaxy groups form and evolve, suggesting that the early universe might have had more structure and organization than previously thought. Our satellite system is constantly changing as new members are discovered and existing ones are torn apart by tidal forces. Recent surveys have revealed extremely faint satellite galaxies that are barely more luminous than large star clusters, pushing the boundaries of what we consider a true galaxy. But even our impressive collection of satellite galaxies is dwarfed by the streams of gas and debris flowing between them. Trailing behind the Magellanic Clouds like a cosmic contrail stretches one of the largest structures associated with our galaxy. The Magellanic Stream is a river of hydrogen gas extending over 600,000 light-years across our sky, longer than the diameter of our entire galactic disk. This enormous streamer of material tells the story of a slow-motion collision that has been unfolding for billions of years. The stream formed through gravitational theft on a galactic scale. As the large and small Magellanic Clouds orbit our galaxy, the Milky Way's superior gravitational pull strips away their outer layers of gas and stars. This stolen material doesn't fall directly into our galaxy. Instead, it gets stretched into long tidal tails that trace the orbital path of the Magellanic Clouds through space. But the Magellanic Stream isn't just a single tail of debris. Recent observations have revealed it's actually a complex network of gas streams, some flowing toward the Milky Way and others being flung outward into intergalactic space. The gravitational interactions between the large and small Magellanic Clouds themselves contribute to this complexity as the two satellite galaxies pull material from each other while simultaneously losing gas to our galaxy's tidal forces. The stream contains enough material to build 2 billion stars like our Sun. That's more gas than exists in many entire galaxies, all stretched across hundreds of thousands of light-years of space. As this material eventually falls into the Milky Way over the next few billion years, it will trigger new episodes of star formation throughout our galactic disk. What makes the Magellanic Stream even more remarkable is its chemical composition. The gas stripped from the Magellanic Clouds contains fewer heavy elements than the material in our galaxy's disk. When this relatively pristine gas mixes with the Milky Way's processed material, it dilutes the concentration of heavy elements and provides fresh fuel for star formation. This ongoing gas recycling process helps explain why our galaxy can continue forming new stars billions of years after its initial formation. The stream also contains dark matter stripped from the Magellanic Cloud's halos. This invisible component helps bind the gas streams together and influences their orbital dynamics. Computer simulations suggest that dark matter streams from disrupted satellite galaxies might be responsible for some of the substructure detected in our galaxy's dark matter halo. Astronomers can use the Magellanic Stream as a probe of our galaxy's gravitational field and dark matter distribution. The precise shape and motion of the stream depend on the total mass of the Milky Way and how that mass is distributed in space. By mapping the stream's structure in detail, researchers can weigh our galaxy and test theories about dark matter's properties. The Magellanic Stream represents just one example of the ongoing merger and accretion processes that have shaped our galaxy throughout cosmic history. Similar streams from other disrupted satellite galaxies crisscross the Milky Way's outer regions, providing evidence that galaxy formation is an ongoing process rather than a single ancient event. But all these gradual changes pale in comparison to the cosmic collision that awaits us in the future. In 4.5 billion years, our night sky will transform into something unrecognizable. The Andromeda Galaxy, currently racing toward us at 250,000 miles per hour, will collide with the Milky Way in the most spectacular cosmic event our galaxy will ever experience. This collision will reshape both galaxies, flinging stars into new orbits and potentially triggering the largest burst of star formation in either galaxy's history. Don't let the word collision fool you. When galaxies collide, individual stars almost never actually hit each other. The distances between stars are so vast that most would pass through the chaos unaffected. Instead, it's a collision of gravitational fields, gas clouds, and dark matter halos. The overall structure of both galaxies will be completely transformed, but the process will unfold over hundreds of millions of years. Andromeda is the largest galaxy in our local group, containing roughly 1 trillion stars compared to our galaxy's 400 billion. It's also approaching us nearly head-on, which will make the collision even more dramatic than if the galaxies were to experience a glancing blow. Computer simulations suggest the initial encounter will send streams of stars flying out into intergalactic space, creating spectacular tidal tails hundreds of thousands of light-years long. The supermassive black holes at the centers of both galaxies will eventually spiral toward each other, creating one of the most energetic events possible in the universe. As these monsters orbit closer and closer together, they'll generate gravitational waves that will ripple through space-time itself. The final merger of the black holes will release more energy in gravitational waves than all the stars in both galaxies combined produce in light. Our solar system will likely survive this cosmic reshuffling, though our location within the galaxy will probably change dramatically. The Sun and its planets might get flung to the outer regions of the merged galaxy, or we could end up closer to the new galactic center. The good news is that by the time this collision occurs, the Sun will be entering its red giant phase anyway, so Earth's habitability will already be compromised by our star's evolution. The collision will also trigger massive bursts of star formation as gas clouds from both galaxies collide and compress. These starbursts will light up the merged galaxy with the brilliance of billions of new stars, creating one of the most luminous objects in the local universe. The star formation rate could increase by factors of hundreds compared to current levels. Astronomers have already given this future merged galaxy a name, Milkomeda. It will likely be an elliptical galaxy rather than a spiral, as the collision will disrupt the organized rotation patterns that maintain spiral structure. The new galaxy will be larger and more massive than either of its parents, containing the combined stellar populations of both the Milky Way and Andromeda. But even this cosmic catastrophe represents just one phase in the long-term evolution of our galactic home. Over timescales so vast they dwarf the current age of the universe, the Milky Way will gradually fade away as its stars burn out one by one, leaving behind a cold, dark cemetery of stellar corpses drifting through an ever-expanding cosmos. The death of our galaxy will unfold over trillions of years, but the process has already begun. Our galaxy's star formation rate has been declining for billions of years as the supply of fresh gas gets depleted. Most of the hydrogen and helium available for making new stars has already been consumed or expelled from the galaxy by stellar winds and supernova explosions. Within about 10 billion years, the Milky Way will stop forming new stars entirely, becoming what astronomers call a red and dead galaxy. As star formation ceases, the galaxy's population will age dramatically. The massive, bright blue stars that currently dominate stellar nurseries will have long since exploded as supernovae. Medium-sized stars, like our Sun, will evolve into red giants, then shed their outer layers to become white dwarf stars. The galaxy will gradually grow redder and dimmer as only the longest-lived, smallest stars continue to burn. Red dwarf stars, the most common type in our galaxy, can burn for trillions of years. These tiny, cool stars will be the last lights shining in the aging Milky Way, providing dim illumination for cosmic timescales that stretch human imagination. But even these stellar survivors will eventually exhaust their nuclear fuel and fade to brown dwarf remnants. The supermassive black hole at our galaxy's center will play an increasingly important role as the galaxy ages. Without fresh gas inflow to feed star formation, material will gradually spiral inward toward the central black hole. Stars that venture too close will be torn apart by tidal forces, briefly flaring as their material gets consumed. Eventually, the black hole will devour a significant fraction of the galaxy's remaining mass. On even longer timescales, the expansion of the universe itself will begin to tear our galaxy apart. Dark energy, the mysterious force driving cosmic acceleration, will eventually overcome the gravitational forces holding the Milky Way together. Individual star systems will be carried away from each other by the expanding fabric of space itself. The final chapter in our galaxy story involves the evaporation of its remaining black holes through Hawking radiation. This quantum mechanical process causes black holes to leak energy and shrink over periods measured in Google years, numbers so large they're written with more zeros than there are atoms in the observable universe. When the last black hole evaporates, it will mark the end of the Milky Way's existence. But perhaps death isn't the right word for this cosmic transformation. The matter and energy that once made up our galaxy will persist in new forms, possibly contributing to entirely different structures in a universe we can barely imagine. The carbon, oxygen, and other heavy elements forged in our galaxy's stars will continue to exist, potentially serving as building blocks for whatever comes next in the cosmic story. Yet, even in its eventual fate, our galaxy remains part of something much larger and more magnificent. The Milky Way is impressive, but it's barely a speck compared to some of the galactic giants lurking in the deeper universe. Scattered across the cosmos are galaxy monsters so massive they make our home look like a cosmic minnow. These galactic behemoths contain hundreds of trillions of stars, stretch for millions of light years, and harbor black holes so massive they could swallow our entire solar system millions of times over. The largest known galaxy is IC 1101, a giant elliptical galaxy that spans over 5 million light-years from end to end. To put that in perspective, the distance from our galaxy to Andromeda could fit inside this monster more than 20 times. IC 1101 contains an estimated 100 trillion stars, making it roughly 250 times more massive than the Milky Way. If our galaxy were the size of a basketball, this galactic giant would be larger than a football stadium. But size isn't the only way galaxies can be monstrous. Some galaxies shine with the combined light of thousands of normal galaxies, powered by supermassive black holes actively feeding on vast quantities of gas and dust. These objects, called quasars, can be detected from billions of light years away because they outshine everything else in their cosmic neighborhood. The black holes powering these beacons can contain the mass of tens of billions of suns. One of the most extreme examples is the galaxy at the center of the Phoenix cluster, which is forming new stars at a rate 500 times faster than the Milky Way. This galactic monster is converting gas into stars so rapidly that it's building the equivalent of several solar masses worth of new stars every single day. At this rate, it could double its stellar population in just a few 100 million years. Then there are the galaxy clusters themselves, gravitational monsters that contain thousands of individual galaxies. The Coma cluster harbors over 1,000 large galaxies and thousands of smaller ones, all bound together by dark matter halos containing the mass of a quintillion suns. These clusters represent the largest gravitationally bound structures in the universe. Perhaps the strangest galactic monsters are the ones that shouldn't exist according to our understanding of cosmic evolution. Astronomers have discovered fully mature, massive galaxies that formed when the universe was less than 1 billion years old. These ancient giants somehow managed to build up enormous stellar populations in a fraction of the time it should have taken, challenging our theories about how galaxies form and grow. Some galaxies even engage in cosmic cannibalism, growing larger by devouring their smaller neighbors. The galaxy M87 contains evidence of having consumed dozens of smaller galaxies over billions of years, building up its current mass of 6 trillion suns through galactic gluttony. Our Milky Way, with its modest 400 billion stars and civilized spiral structure, represents just one small example of what galaxies can become. We live in a relatively quiet cosmic neighborhood, but the universe contains galactic monsters that dwarf anything in our local experience. These cosmic giants help us understand our own galaxy's place in the vast hierarchy of cosmic structures. After traveling from our local solar neighborhood to the very edge of the Milky Way and beyond, it's time to zoom out one final time and see where we truly live in the cosmic hierarchy. Our complete cosmic address reads like a map of nested structures, each one larger and more magnificent than the last, stretching from the familiar to the almost incomprehensibly vast. We start with Earth, orbiting the Sun in a solar system located in the local bubble, within the Orion arm of the Milky Way galaxy. But that's just the beginning of our address. Our galaxy belongs to the local group, a collection of over 80 galaxies dominated by the Milky Way, Andromeda, and Triangulum. This entire group spans about 10 million light-years and contains roughly 3 trillion stars. The local group, in turn, sits on the outskirts of the Virgo cluster, a massive collection of over 2,000 galaxies centered about 54 million light-years away. The Virgo cluster contains some of the largest galaxies known, including the giant elliptical M87 with its 6.5 billion solar mass black hole. Our local group is slowly falling toward this cluster, accelerated by its immense gravitational pull. But even the Virgo cluster is just a small part of something much larger. It sits near the center of the Virgo supercluster, also called the local supercluster, a vast sheet of galaxies and galaxy clusters stretching across 110 million light-years. This structure contains roughly 100,000 galaxies and represents one of the largest coherent structures in the nearby universe. Recent discoveries have revealed that our supercluster is itself part of an even larger structure called Laniakea, Hawaiian for immeasurable heaven. This supercluster of superclusters spans 500 million light-years and contains the mass of 100 quadrillion suns. The gravitational center of Laniakea, called the Great Attractor, is pulling our entire local group toward it at over 1 million miles per hour. But the cosmic hierarchy doesn't stop there. Laniakea connects to other superclusters through vast filaments of dark matter and galaxies, creating a cosmic web that spans the observable universe. Between these filaments lie enormous voids, cosmic deserts containing almost no galaxies at all. Some of these voids are so large that light takes hundreds of millions of years to cross them. Your complete cosmic address therefore reads Earth, Solar System, Local Bubble, Orion Arm, Milky Way Galaxy, Local Group, Virgo Cluster, Local Supercluster, Laniakea Supercluster, Observable Universe. Each level of this address represents structures that are home to increasingly vast numbers of stars, planets, and potentially other forms of life. Understanding our place in this cosmic hierarchy puts everything in perspective. The journey we've taken from Earth to the galactic center and beyond represents just one tiny thread in the vast cosmic web. Yet within that web, on a small rocky planet orbiting an ordinary star, something extraordinary has happened. Matter has organized itself into forms complex enough to contemplate its own existence and map the very structures that contain it. We are the universe becoming aware of itself, one galaxy at a time. We began this journey 26,000 light-years from home, racing through space at 500,000 miles per hour. We've witnessed stellar nurseries giving birth to giants, explored the hidden architecture of spiral arms, and stared into the face of a monster black hole that anchors our entire galaxy. From the quiet bubble of space around our solar system to the cosmic web that connects superclusters across hundreds of millions of light-years, we've traced the path from the familiar to the almost unimaginable. The Milky Way isn't just our cosmic home, it's a dynamic, evolving system where matter and energy dance on scales that stretch human comprehension. Every element in your body was forged in the nuclear furnaces of stars that lived and died long before our solar system existed. You are literally made of galactic recycled material, assembled from stellar ash that has journeyed across space and time to become part of something capable of understanding its own origins. But perhaps the most remarkable discovery from our galactic odyssey is how much we still don't know. Dark matter outweighs everything we can see by 10 to 1, yet its nature remains completely mysterious. The supermassive black hole at our galaxy's heart follows the laws of physics into realms where space and time themselves break down. The cosmic web that connects galaxy clusters across the universe appears to be accelerating apart due to an even more mysterious dark energy. We live in an age of cosmic discovery unprecedented in human history. Every year brings new revelations about our galactic home, from the detection of gravitational waves rippling through spacetime to direct images of black hole event horizons. The James Webb Space Telescope is revealing galaxies from when the universe was young, while ground-based observatories map the motion of individual stars around our galaxy's central black hole. Yet, for all our cosmic knowledge, we remain the only known observers in this vast galactic theater. In a galaxy containing 400 billion stars, on a planet perfectly positioned in the galactic habitable zone, matter has organized itself into forms complex enough to contemplate its own existence and map the very structures that contain it. We are the universe becoming aware of itself, one galaxy at a time. The next time you look up at the night sky, remember that you're seeing just the nearest edge of a galactic city containing more stars than grains of sand on all Earth's beaches. You're orbiting one of those stars at 500,000 miles per hour, carried along by gravitational forces that reach across the galaxy to touch our motion. The calcium in your bones was forged in stellar explosions, the iron in your blood was cooked in the cores of dying giants, and the oxygen you breathe was scattered by cosmic winds billions of years ago. Our journey to the center of the Milky Way reveals that we don't just live in the universe, we are the universe, organized into temporary patterns capable of mapping our own cosmic context. In understanding our galaxy, we understand ourselves. Subscribe for more cosmic journeys. And remember, you are made of stars. Good night.